Hello viewers, in today's session we are going to discuss an important problem from inverse Laplace transform, and in this class we are going to find out the inverse Laplace transform of this function, that is 1 over s plus 2 raised to 5. So here we are going to discuss an important property of inverse Laplace transform of derivatives. Right now, see, suppose we have a function, say f of t, whose Laplace transform is given by f of s. Right, then the inverse Laplace transform of the nth derivative of f of s, that is fn. Here n denotes the nth derivative, and the inverse Laplace transform of the function, that is f of s, is given by a minus 1 raised to n. Then we have t raised to n, and here we have the function f of t, and n it takes the values 1, 2, 3, and so on. Right, so if we have the Laplace transform of a function f of t as f of s, then the inverse Laplace transform of nth derivative of f of s is given by this expression, that is minus 1 raised to n t raised to n f of t. Right, and here the nth derivative of f of s may also be denoted by this notation, that is dn, and here we have dsn, and here we have f of s. So to get the inverse Laplace transform of this function, we are going to utilize this property. So now from this expression, let us write the inverse Laplace transform of f of s is equal to f of t. Right, so now if we compare this expression with this one, then here we can write f of s as this function, that is 1 over s plus 2 raised to 5. Right, so that we can write the inverse Laplace transform of 1 over s plus 2 raised to 5 is equal to f of t, and here we assume f of s as 1 over s plus 2 raised to 5. So now let us consider a function, say g of s, that is equal to 1 over s plus 2. Right, and let us differentiate g of s with respect to s. So g prime of s is given by the derivative of 1 over s plus 2 with respect to s, and we can write d by ds of s plus 2 raised to minus 1, that is equal to minus 1 over s plus 2 whole square. Right, now let us take the second derivative of g of s, that is g double prime s, and we have minus d by ds of this expression. So we have here s plus 2 raised to minus 2. So now we can write minus, and then we have minus 2 over s plus 2 raised to minus, here we have positive 3. Right, so here we can now write plus 3, and this is plus 2, and we have s plus 2 raised to 3. So now let us take the third derivative of g of s. So we have g triple prime here, and we have 2 d by ds of s plus 2 raised to minus 3. So we have 2, and here we have minus 3 over s plus 2 raised to 4, and this is minus 6 over s plus 2 raised to 4. Now let us take the fourth derivative of g of s. So the fourth derivative of g of s may be denoted by g4s, and here we have minus 6 d by ds of s plus 2 raised to minus 4. So this is minus 6 times minus 4 over s plus 2 raised to 5, and this is minus times minus is positive, and here we have 24 over s plus 2 raised to 5, right? So the fourth derivative of g of s is given by 24 divided by s plus 2 raised to 5, and here we can see that we have arrived at this expression, that is 1 over s plus 2 raised to 5, right? So now we'll not find out the uh, further derivatives, and will now apply this property. So now let us write it as 24 times 1 over s plus 2 raised to 5, and 1 over s plus 2 raised to 5 is f of s. So we have here 24 times f of s, right? So now we have the fourth derivative of g of s, that is equal to 24 times f of s. So now let us take the inverse Laplace transform of both sides. So we can now write here inverse Laplace transform of the fourth derivative of g of s, and here we have the inverse Laplace transform of 24 times f of s. So we can take 24 outside, so we have here 24 times the inverse Laplace transform of f of s, right? And f of s is 1 over s plus 2 raised to 5. So we can now write here the inverse Laplace transform of f of s, taking f of s as s plus 2 1 over s plus 2 raised to 5, and here we can take 1 over 24 times the inverse Laplace transform of the fourth derivative of g of s. So now consider this expression. So here inverse Laplace transform of fourth derivative of g of s, and here we have the inverse Laplace transform of the nth derivative of f of s. So using this result for this function, right? So we can now write 1 over 24, and then we have minus 1 raised to n. So n is equal to 4, so we have minus 1 raised to 4, then we have t raised to 4, and f of t. Now see, f of t is the inverse Laplace transform of f of s, and here we are considering the function g of s. So let us consider the inverse Laplace transform of this function g of s equal to some function, say capital G of t, right? So here we are taking capital F of t and small f of s, and here we have capital G of t, and here we have small g of s, right? So we can now write the Laplace transform of this function g of t is equal to g of s, that is equal to 1 over s plus 2. Now from the Laplace transform of some standard functions, we know that the Laplace transform of e raised to say at is given by 1 over s minus a. So if we take a is equal to minus 2, then the Laplace transform of e raised to minus 2t is given by 1 over s minus minus 2, that is 1 over s plus 2, right? And 1 over s plus 2 is equal to g of s, right? So if we now compare this expression with this one, then here we can now see that g of t is our function, the exponential function e raised to minus 2t. So now let us come to this expression. So here we have 1 over 24 minus 1 raised to 4, then t raised to n, that is t raised to 4. And for f of t, now we have to write here g of t, right? Because g of t is corresponding to this small g of s, right? And g of t is e raised to minus 2t, so we can now write 1 over 24 minus 1 raised to 4 is simply plus 1. This is t raised to 4, and here we have e raised to minus 2t. So this is equal to 1 over 24 times t raised to 4 and e raised to minus 2t. So the inverse Laplace transform of 1 over s plus 2 raised to 5 is given by this expression using this important property of inverse Laplace transform.